across and up. But if these movements are happening simultaneously, then you can have 64 possible combinations of movements. But in this performance called Movatar, what we constructed was an avatar imbued with genetic algorithms whose behavior evolved during the performance. So as the avatar sort of changed its bodily movements, so it affected my physical body. So in this performance, the upper part of my body was avatar actuated, whilst the lower part was free to perform with my own agency. And in this performance, the body itself becomes a kind of prosthesis, enabling the behavior of an avatar in the real world. A kind of inverse motion capture system. In motion capture, there are electrodes on this body. If I move, I can activate a computer model. But imagine if the opposite is possible. If an avatar imbued with a rudimentary intelligence can access a physical body and perform with it in the real world, this would be a sort of an interesting interface, an inverse motion capture system. Okay, and exoskeleton. Although the initial interest was in the use of manipulators, I was always intrigued with insect locomotion. And we constructed in Hamburg with a group of artists called F18 a six-legged walking machine that was able to carry my body. The movements of the machine are controlled by the upper body exoskeleton that allowed the computer to recognize the different arm gestures and thereby select the different leg movements. This performance was a performance where you translate arm movements into machine leg motions. Sound was also important in this performance, the sound registering the motion of the machine, but also indicating the direction and the orientation of the robot. So it was a kind of hybrid human-machine system. Was that if I lifted one leg up, 3 robot legs would lift and swing forward. If I lifted the other leg up, the other 3 legs would lift and swing forward. So simply by stepping up and down on the spot, the machine would walk. Unfortunately, with this particular design, the machine took a few steps forwards and fell over sideways. It was never realized as a successful mechanism. So we tried different kinds of approaches, and the final design of this new walking machine was more in this way, that the body is actually within the chassis of the machine. And what happens here is that the human bipedal gait is translated into this 6-legged walking insect-like machine. And also we used pneumatic rubber muscles. So instead of pneumatic steel actuators, these rubber muscles would expand in girth, contract 20% of their length, producing a strong pulling force. So this kind of muscle machine was used in a performance in London in 2003. So this is in fact much closer to what was the reality of the machine. And with the pneumatic rubber muscles, even though this robot was 5 meters in diameter, it was 200 kilograms lighter than the previous exoskeleton robot. A more recent project is the Walking Head project. This is only a 2-meter diameter robot mounted with an LCD screen imaging a human head. And this robot is a kind of virtual actual system where the behavior, the facial behavior of the computer-generated head is activated and modulated by the leg movements. It had an ultrasound scanning device to detect the presence of anyone in the gallery. So ordinarily the robot is sitting, doing nothing, until someone comes into the gallery. Then the robot detects that person, stands, selects from its library of possible movements and performs a choreography for a few minutes. Then it sits down and waits for the next person. Sound for this, please. Sound.
Our robotics laboratory at Case Western Reserve University. Our near-term robots use abstracted insect locomotion principles, whereas our advanced legged vehicles are more directly based upon insects. Both of these lines of vehicles can be scaled up or down in size to suit specific mission requirements. Our larger near-term robots use 6 appendages driven by a single motor in a nominal alternating tripod gait like that used by insects.